January 17, 1940. The morning frost clung to the window panes of the Kaiser Wilhelm Institute of Metals Research in Berlin as Dr. Heinrich Cornelius adjusted his wire-rimmed spectacles and opened the leather-bound report before him. The document, stamped with the Reich Ministry seal, contained metallurgical assessments of potential enemy industrial capabilities. Steam rose from his coffee cup, mingling with the cigarette smoke that perpetually clouded the laboratory where Germany's finest minds analyzed the molecular structure of warfare itself. The report's pages rustled in the winter silence. American steel production statistics, compiled by German industrial spies and trade attachés, filled column after column with what seemed like impossible numbers. 26 million tons annually in 1938 alone. Dr. Cornelius shook his head, the gesture carrying the weight of scientific skepticism that had made German engineering the envy of the world. These Americans, he reasoned, surely prioritized quantity over the precision that defined German metallurgy. Their crude blast furnaces could never match the sophisticated Krupp steel that formed the backbone of the Wehrmacht's Panzers. Outside, snow began to fall on a Berlin that believed itself invincible, where scientists in white laboratory coats held the molecular keys to conquest. Inside the institute, test samples of German armor steel gleamed under tungsten lights, each piece a testament to face-hardened perfection, to carbon content calculated to the third decimal place, to a metallurgical philosophy that prized engineered superiority over mass production. The Americans, Dr. Cornelius noted in his daily log, appeared to be building steel the way they built everything else: fast, cheap, and without the Germanic dedication to perfection that had defined industrial excellence for generations. The coffee had grown cold by the time he reached the final page, but the conclusion remained unchanged. American steel might flow like a river, but German steel was forged like a blade. Precision crafted, scientifically superior, and ultimately decisive. The numbers on those pages represented raw tonnage, nothing more. Quality, as every German engineer knew, would always triumph over quantity when the crucible of war tested the molecular bonds that held civilization together. This was the morning when confidence crystallized into doctrine, when scientific hubris merged with national pride to create a certainty that would shape the greatest industrial conflict in human history. Dr. Cornelius closed the report, unaware that his assumptions about American steel would soon be shattered by the very metal he had so casually dismissed. The frost on his window began to melt as Berlin awakened to another day of preparation for a war where steel would write the verdict in language more brutal than any scientist could imagine. The German scientific community's assessment of American industrial capacity in 1940 reflected decades of accumulated prejudice masquerading as technical analysis. Germany's metallurgists, chemists, and engineers had built their reputations on precision, the methodical development of face-hardened armor that combined a brittle outer shell with a ductile inner core, creating heterogeneous steel that could shatter incoming projectiles while absorbing their kinetic energy. This was the triumph of the Krupp method, the metallurgical philosophy that had armored the Kaiser's dreadnoughts and now protected the Reich's Panzers. American steel, by contrast, appeared primitive in German technical journals, where German armor plates were flame-hardened using expensive oxyacetylene torches, applying precisely controlled heat to achieve optimal carbon diffusion patterns. American producers seemed content with simple rolled homogeneous armor, steel that was merely heated, rolled and cooled without the sophisticated surface treatments that marked advanced metallurgy. German scientists read reports of American blast furnaces operating at maximum capacity with minimal quality control, churning out steel that prioritized production speed over molecular perfection. The numbers themselves seemed to confirm German superiority. Krupp steel contained carefully calibrated carbon levels between 0.26 and 0.53%, with chromium additions reaching 3.2% to enhance hardness and corrosion resistance. Each plate underwent rigorous testing, with hardness measurements recorded to ensure optimal ballistic performance. American steel specifications, obtained through industrial espionage, showed looser tolerances, less exotic alloy compositions, and production methods that emphasized throughput over precision engineering. Fritz Todt, the Reich's Minister of Armaments until his death in February 1942, had been among the few German officials to seriously study American industrial potential. His reports, largely ignored by the Nazi leadership, warned that American production capacity could prove decisive in any extended conflict. But even Todt's warnings focused on volume, rather than quality, the assumption that American industry could produce vast quantities of inferior equipment that might eventually overwhelm German technological superiority. Through sheer numerical advantage, German tank designers embraced this confidence when developing the Panzer IV, Panther, and Tiger series. The Panther's frontal armor, sloped at 55 degrees and measuring 80 millimeters thick, incorporated face-hardened steel designed to defeat any known Allied anti-tank weapon. The steel itself contained high carbon levels, up to 0.75% in some samples, creating maximum surface hardness when properly heat-treated. German metallurgists calculated that this heterogeneous armor would prove superior to simple homogeneous steel of equivalent thickness, particularly when fighting at the extended ranges where German optics and gun accuracy provided additional advantages. The industrial infrastructure supporting this metallurgical philosophy stretched across the Reich, from the Ruhr Valley's coal mines to the precision machinery works of Bavaria. German steel production peaked at approximately 22.5 million tons in 1940, a figure that represented not just raw capacity, but technological sophistication. Steel produced according to specifications that governed every aspect of alloy composition, heat treatment, and quality control. Each ton represented the culmination of decades spent perfecting the molecular science of warfare. This was the foundation of German confidence as the Wehrmacht prepared for global conquest. Their scientists possessed superior knowledge, their engineers designed better systems, and their metallurgists produced higher quality materials than any potential enemy. The Americans might build more steel, but German steel would prove decisive when quality met quantity on the battlefields of Europe. The molecular bonds within each armor plate carried the weight of national destiny, scientific pride, and the unshakable belief that precision engineering would always triumph over mass production. Yet even as German scientists celebrated their technological supremacy, American blast furnaces were beginning to reshape the fundamental equations of industrial warfare. In Pittsburgh, Gary, and Birmingham, a different metallurgical philosophy was taking shape, one that would challenge every assumption the Germans had made about steel, warfare, and the relationship between quality and quantity in the crucible of total war. The German expectation of American industrial performance rested on decades of perceived evidence that seemed to confirm their biases about American engineering. German technical delegations visiting American steel plants in the 1930s filed reports describing production methods that prioritized speed and volume over the methodical precision that characterized German manufacturing. They observed American workers operating machinery with what seemed like casual indifference to the molecular perfection that German metallurgists demanded from every steel ingot. These observations shaped military planning as Germany prepared for war. Wehrmacht strategists calculated that American tanks, even if produced in large numbers, would prove vulnerable to German anti-tank weapons specifically designed to defeat homogeneous armor. The German 7.5 cm K-42 gun mounted on the Panther tank could penetrate 138 millimeters of vertical armor at 1,000 meters, more than sufficient to defeat any known American tank. German gunners trained extensively on range estimation and target engagement. confident that their superior optics and ballistic calculations would allow them to destroy multiple American tanks before sustaining significant losses themselves. The expectation extended beyond mere mechanical considerations to encompass broader assumptions about American industrial culture. German engineers had built their careers on exhaustive testing, meticulous documentation, and incremental improvements to proven designs. American industry, they believed, operated according to different principles: rapid prototype development, good enough engineering solutions, and cost-cutting measures that sacrificed performance for affordability. This cultural assessment reinforced technical conclusions about steel quality and tank effectiveness. German tank crews received training that emphasized their technological advantages over potential American opponents. Panzer commanders learned to identify Sherman tanks by silhouette, studied their armor thickness distributions, and practiced engagement techniques designed to exploit perceived weaknesses in American design philosophy. The training manuals stressed that American tanks, while numerous, represented quantity over quality, mechanical reliability rather than battlefield superiority. This confidence permeated every level of German armor doctrine. Tank battalion commanders developed tactics that assumed numerical inferiority but technological supremacy, planning to defeat larger American formations through superior positioning, better armor protection, and more effective gunnery. The German military-industrial complex had produced panzers that could defeat multiple American tanks in any engagement, making numerical disadvantages irrelevant when quality advantages were properly exploited. But when German tank crews first encountered American armor in North Africa during 1942, the reality proved more complex than their expectations had suggested. The M4 Sherman tanks facing German Panzers carried 75mm guns capable of penetrating German armor at combat ranges, while their own armor proved more resilient than German intelligence had predicted. The homogeneous steel that German scientists had dismissed as primitive demonstrated superior performance against certain types of anti-tank rounds, particularly when struck at angles that favored the defender. More disturbing were reports from German tank crews describing the mechanical reliability of American tanks. While German panzers suffered from complex drivetrains, temperamental final drives, and maintenance requirements that demanded highly trained technicians, American Shermans operated with mechanical simplicity that allowed rapid field repairs and extended operational availability. German expectations of American mechanical inferiority proved unfounded when Sherman tanks continued operating under conditions that would have sidelined more sophisticated German vehicles. The first cracks in German confidence appeared not through dramatic battlefield defeats, but through accumulating evidence that American steel performed better than predicted. American tanks proved more capable than expected, and American production methods yielded results that contradicted German assumptions about the relationship between engineering sophistication and combat effectiveness. The molecular structure of confidence began to fracture as reality intruded upon scientific certainty. Yet the most profound shock to German expectations would come not from individual tank encounters, but from the sheer scale of American production, steel output that dwarfed German capacity, tank production that replaced losses faster than German forces could inflict them, and industrial methods that combined adequate quality with overwhelming quantity to reshape the fundamental mathematics of armored warfare. The transformation of German perceptions began with small, disturbing details that accumulated like stress fractures in armor plate. Tank recovery crews reported that, knocked out, Sherman tanks often showed clean penetrations through their homogeneous armor, holes that indicated successful hits, but also revealed steel that maintained its structural integrity even when defeated. German panzers, struck by American anti-tank rounds, by contrast, frequently suffered catastrophic armor failures where face-hardened plates cracked and spalled across wide areas, creating damage patterns that made repair impossible and recovery dangerous. Dr. Cornelius received his first detailed combat reports in late 1943, documents that forced him to reconsider fundamental assumptions about metallurgy and warfare. German ballistics experts had captured several Sherman tanks for detailed examination, cutting away armor sections to analyze their molecular structure under laboratory conditions. The results challenged everything German science had assumed about American steel quality. The American armor plates showed uniform grain structure throughout their thickness, indicating proper heat treatment and quality control that matched German standards. More surprisingly, the homogeneous steel demonstrated superior performance against capped armor-piercing rounds, exactly the type of ammunition German tanks used most frequently. Where German face-hardened armor tended to crack catastrophically when its hard outer layer was breached, American homogeneous steel deformed plastically, containing damage and maintaining structural integrity even after penetration. Testing revealed another unsettling truth. American steel contained fewer impurities than many German samples. While German armor from 1943 onward showed increasing sulfur content, up to 0.22% in some Panther tanks, indicating wartime compromises in raw material quality, American steel maintained consistent chemical composition that suggested both adequate raw materials and effective quality control procedures. The Americans were not merely producing more steel, they were producing better steel than German intelligence had predicted. German metallurgists discovered that American steel plants had adopted production methods that achieved both high quality and high quantity through systematic approaches to manufacturing that German industry had not anticipated. Where German scientists had assumed that rapid production necessarily meant compromised quality, American plants demonstrated that properly designed industrial processes could maintain metallurgical standards while dramatically increasing output rates. The psychological impact of these discoveries rippled through German scientific and military communities. Engineers who had built their careers on assumptions of German technological supremacy found themselves confronting evidence that their fundamental beliefs about American industrial capability had been wrong. The implications extended beyond metallurgy to encompass broader questions about German technical leadership, industrial planning, and military strategy. Field reports from Panzer commanders reinforced laboratory findings with battlefield evidence. German tank crews reported that Sherman tanks continued fighting effectively even after sustaining multiple hits, while their own Panzers often suffered mobility kills from single penetrating rounds that caused armor to crack and spall internally. The superior mechanical reliability of American tanks meant that more Shermans remained operational during extended engagements, offsetting individual technical advantages that German tanks might possess. Most troubling were reports about American tank production rates. German intelligence estimates had predicted that American industry might produce several hundred tanks monthly, but captured documents revealed production figures that seemed impossible. Thousands of tanks rolling off assembly lines each month, with individual plants exceeding Germany's total monthly output. The scale of American production meant that German forces faced not just better tanks than expected, but vastly more tanks than anyone had thought possible. The cumulative effect of these revelations transformed German understanding of their strategic position. What had begun as a contest between German quality and American quantity had evolved into a confrontation where American industry achieved both superior quality and overwhelming quantity simultaneously. German scientists found themselves forced to acknowledge that their pre-war assessments had been not merely incomplete, but fundamentally incorrect about American industrial capability. The transformation accelerated as German forces encountered American weapons systems that incorporated metallurgical advances German science had not anticipated. The 76mm guns mounted on later Sherman variants could penetrate German armor at ranges that made German tactical advantages irrelevant, while American armor-piercing ammunition demonstrated ballistic performance that exceeded German predictions. Each encounter provided additional evidence that American industrial capability had been systematically underestimated by German technical intelligence. By 1944, the weight of accumulated evidence had forced a complete reversal in German scientific opinion about American steel and industrial capacity. The Americans had not simply matched German quality while exceeding German quantity, they had developed industrial methods that achieved both objectives simultaneously through systematic approaches to manufacturing that German industry struggled to replicate, even under ideal conditions. The mathematical reality of American steel production became undeniable as German forces confronted its results. Across multiple theaters of war. In 1943, American blast furnaces produced approximately 80 million tons of steel, nearly 4 times Germany's peak wartime output. But the truly staggering revelation came when German intelligence analyzed regional production figures that revealed the depth of American industrial capacity. The Pittsburgh metropolitan area alone produced more steel than many entire nations, including some of Germany's allies. Pittsburgh's mills, centered along the Monongahela River, had achieved production rates that defied German understanding of industrial possibility. The city's integrated steel works combined coal from Pennsylvania mines, iron ore from the Great Lakes region, and transportation networks that moved raw materials and finished products with efficiency that German logisticians had not imagined possible. By 1944, the Pittsburgh region was producing over 25 million tons of steel annually, more than the entire German Reich at its wartime peak. The scale became personal for German tank crews when they realized that individual American steel plants could outproduce entire German industrial regions. The Gary Works in Indiana, a single integrated facility, produced more armor plate steel in 1 month than German plants could manufacture in 6 months of maximum effort. These were not statistical abstractions, but battlefield realities that manifested in the form of seemingly endless streams of American tanks, artillery pieces, and ammunition that German forces encountered across Europe. German intelligence reports documented American production capabilities that reached beyond mere numbers to encompass industrial methods that German engineers struggled to comprehend. American steel plants operated continuously, with production lines that never stopped for retooling or maintenance, achieving capacity utilization rates that German industry could not match even under wartime emergency conditions. The Americans had industrialized steel production to a degree that transformed manufacturing from craftsmanship into systematic engineering. The evidence extended beyond steel to encompass the entire American military-industrial complex. German forces captured American equipment that revealed manufacturing quality and consistency across thousands of identical units, tanks that showed uniform armor thickness, identical component specifications, and standardized performance characteristics that indicated quality control procedures operating at unprecedented scale. Each captured Sherman tank represented not just one vehicle, but proof of industrial capability that could produce thousands of identical vehicles to the same specifications. German metallurgists analyzing captured American equipment discovered that the Americans had solved fundamental engineering problems through systematic approaches that German science had not anticipated. American armor welding showed consistent quality across entire production runs, indicating automated processes that maintained standards while achieving production rates that manual methods could never match. The molecular structure of American steel revealed heat treatment procedures that were not just adequate but optimized for specific applications. The psychological impact of these discoveries undermined fundamental assumptions about German technological leadership. Engineers who had dedicated their careers to precision manufacturing found themselves confronting evidence that American industry had achieved precision at scale, combining the quality that German science prized with production volumes that German industry could not approach. The Americans had not sacrificed quality for quantity. They had developed methods that achieved both simultaneously. Combat reports from German tank commanders provided battlefield confirmation of industrial intelligence. American tanks encountered in Normandy showed manufacturing quality that matched or exceeded German standards, while their sheer numbers made tactical victories irrelevant when strategic defeat became inevitable. German panzer battalions that destroyed dozens of American tanks found themselves facing hundreds more the following day, each one manufactured to specifications that indicated systematic quality control procedures. C. Scope of American achievement became clear when German engineers calculated that American steel production in 1944 exceeded the combined output of all Axis powers. The United States alone produced more steel than Germany, Japan, and Italy combined, while maintaining quality standards that German analysis had deemed impossible at such production scales. American industry had redefined the relationship between quality and quantity, achieving both through systematic approaches to manufacturing that German engineering education had not prepared its practitioners to understand. The implications extended far beyond metallurgy to encompass fundamental questions about industrial organization, resource allocation, and the systematic application of engineering principles to manufacturing problems. American industry had achieved results that challenged German assumptions about the limits of industrial possibility, forcing recognition that the contest had never been between German quality and American quantity, but between different approaches to solving engineering problems at industrial scale. As German resistance crumbled under the weight of American industrial output, the steel that had once symbolized German technological supremacy became a monument to industrial miscalculation. The face-hardened armor that German scientists had perfected proved less effective than the homogeneous steel they had dismissed, while American production methods delivered both superior performance and overwhelming numerical advantage. Simultaneously, the story of German scientific certainty confronting American industrial reality found its symbol in a mundane but powerful recurring image: the sound of American steel cutting through German armor. From the beaches of Normandy to the streets of Berlin, German defenders heard the distinctive crack of 70 and 70 cm guns firing armor-piercing rounds that had been manufactured in Pittsburgh, Birmingham, and Gary, steel forged in blast furnaces that operated on scales German industry had never imagined possible. This sound became the audio signature of American abundance, a metallurgical Morse code that transmitted the message of industrial supremacy across every battlefield where German and American forces met. Each crack represented not just a single round, but the entire American industrial complex: the coal mines of Pennsylvania, the iron ore boats crossing the Great Lakes, the blast furnaces that never cooled, and the production lines that turned raw materials into finished weapons with mechanical precision that German scientists had once believed impossible. The sound carried additional meaning for German tank crews who learned to distinguish between different types of American ammunition. The sharp crack of standard armor-piercing rounds differed from the deeper boom of high-velocity armor-piercing rounds, each manufactured to specifications that indicated quality control procedures operating at unprecedented scale. German veterans could identify American guns by their sound signature, an acoustic testament to standardized manufacturing that produced thousands of identical weapons firing millions of identical rounds. German engineers analyzing captured American ammunition discovered manufacturing quality that challenged their assumptions about mass production. American shells showed consistent wall thickness, uniform ballistic performance, and metallurgical properties that indicated sophisticated quality control procedures. The steel casings revealed uniform grain structure, proper heat treatment, and chemical composition that matched specifications across entire production runs. Each round represented proof that American industry had achieved precision manufacturing at scales German production methods could not approach. The sound of American guns became more than mere battlefield noise. It represented the acoustic signature of industrial transformation. German defenders listening to American artillery barrages heard not just explosions, but the sound of American blast furnaces, rolling mills, and production lines that had converted raw materials into military power with efficiency that redefined industrial possibility. Each shell burst carried the molecular signature of American steel, forged according to specifications that prioritized both performance and producibility. The psychological impact of this sound affected German morale in ways that went beyond immediate tactical concerns. Soldiers who had been trained to believe in German technological superiority found themselves confronting acoustic evidence of American industrial supremacy. The continuous sound of American weapons fire represented not just immediate danger but proof that German strategic calculations had been fundamentally wrong about American industrial capability. German tank crews developed tactical responses to American firepower that acknowledged the reality of American steel quality. Panzer commanders learned to avoid direct engagements with Sherman tanks armed with 76mm guns, recognizing that American ammunition could penetrate German armor at ranges that made German advantages in optics and crew training irrelevant. The sound of American guns became a signal to withdraw, seek cover, or abandon positions that had once been considered secure. The acoustic signature of American steel extended beyond individual weapons to encompass entire battlefields. German defenders in Normandy reported continuous sounds of American tanks, artillery, and aircraft that represented industrial output operating at scales German production could not match. The sound environment of American-equipped battlefields differed qualitatively from engagements with other Allied forces, reflecting the unique characteristics of American military-industrial production. As the war progressed, the sound of American steel became the soundtrack of German defeat. From the first penetrations of Atlantic Wall fortifications to the final battles in the streets of Berlin, German forces confronted acoustic evidence of American industrial supremacy that had transformed raw materials into military power through methods German engineering had failed to anticipate. The crack of American guns carried the sound not just of individual battles, but of industrial revolution that had redefined the relationship between technology, production, and warfare itself. The sound echoed through ruined German cities where citizens who had once believed in the superiority of German engineering heard concrete proof that American industry had achieved both quality and quantity simultaneously. Each American shell burst represented the failure of German strategic planning, the inadequacy of German intelligence assessment, and the collapse of scientific certainty that had once seemed unshakable. The molecular bonds within American steel had proven stronger than the intellectual bonds that held German assumptions together. The final accounting of German scientific miscalculation became clear in the ruins of the Reich, where the accumulated weight of American steel production had crushed not just German military resistance, but the entire foundation of assumptions about industrial capability, technological leadership, and the relationship between scientific knowledge and strategic reality. The battle between German quality and American quantity had never been a fair contest because the Americans had refused to accept the terms of engagement that German science had assumed were inevitable. In the spring of 1945, as American tanks rolled through German cities whose steel mills had once symbolized industrial might, the sound of American steel provided a final lesson in the relationship between scientific certainty and historical reality. The crack of guns firing ammunition manufactured in Pennsylvania echoed through streets where German metallurgists had once celebrated their technological supremacy, carrying an acoustic reminder that industrial capability could be systematically developed through methods that transcended traditional approaches to manufacturing and quality control. The story reached its conclusion not with dramatic battlefield confrontations, but with quiet recognition that fundamental assumptions about technology, production, and warfare had been wrong. German scientists who had begun the war confident in their metallurgical superiority ended it confronting evidence that American industry had achieved results their theoretical framework could not explain. The sound of American steel had become the sound of intellectual transformation, forcing recognition that scientific knowledge divorced from industrial reality could produce strategic miscalculations with catastrophic consequences. In the end, the contest between German science and American industry had never been about steel alone, but about different approaches to solving complex problems under extreme conditions. German metallurgists had optimized individual solutions, while American engineers had optimized entire systems, achieving performance advantages that transcended the capabilities of individual components. The crack of American guns represented not just superior firepower but superior systematic thinking about the relationship between scientific knowledge, industrial capability, and strategic objectives. The lesson echoed beyond the immediate context of World War II to encompass broader questions about the nature of technological competition, industrial development, and the systematic application of engineering knowledge to complex problems. American steel had proven superior not because American metallurgists possessed better theoretical knowledge, but because American industry had developed better methods for translating knowledge into practical results at unprecedented scale. The sound of American steel cutting through German armor became a metaphor for the triumph of systematic engineering over individual excellence, of industrial democracy over technological aristocracy, and of abundance over scarcity as organizing principles for modern warfare. The molecular structure of victory had been forged not in individual laboratories but in integrated industrial systems that connected raw materials to finished products through methods that maximized both quality and quantity simultaneously. This transformation represented more than military victory. It marked the emergence of industrial democracy as a strategic advantage that would shape global competition for generations to come. The sound of American steel had announced not just the defeat of German militarism, but the arrival of systematic approaches to technological development that would redefine industrial competition across every field of engineering endeavor. The crack of those guns continues to echo through history as a reminder that scientific knowledge without systematic industrial application remains merely academic exercise, while industrial capability guided by systematic engineering principles can transform theoretical possibilities into strategic realities that reshape the world. American steel had proven that abundance and quality were not competing objectives, but complementary achievements of systematic approaches to solving complex problems under extreme conditions. The final sound was silence, the quiet recognition that assumptions about technological superiority must be constantly tested against the reality of systematic achievement, and that true engineering excellence lies not in perfecting individual solutions, but in developing industrial systems that deliver consistent results at scales that transform strategic possibilities into historical realities. The molecular bonds within American steel had proven stronger than the intellectual bonds that held German assumptions about technological competition together, forging a new understanding of the relationship between scientific knowledge, industrial capability, and strategic success in modern warfare.